Chemical stimuli. As mentioned in the previous section, I wished to discover the cues which contribute to the formation and maintenance of the diurnal aggregations of Clibinarius tricolor and of Pagurus miamensis. During the course of experiments concerned with this phenomenon, several types of reactions to chemical stimuli were discovered. In the case of Clibinarius tricolor, two varieties of the test apparatus were employed. The apparatus used for the great majority of the tests is outlined in Figure 37. During the summer of 1962, a large enamel pan was used in place of the Y-tube employed in all the 1963 tests. Figure 37. Diagram of apparatus used in chemical orientation tests. A population of organisms was established in the right or left tank, test tank. This population was maintained for at least 24 hours before testing began. The rate of flow of the common water supply was maintained at about 100 cc per minute to each tank. The rates of flow from the test and control tanks were maintained at about 45 cc per minute. Although the latter rate was checked quantitatively just a few times, the two outlets were frequently checked for equality of flow. A black plastic partition separated the test and control tanks from the clear plastic Y-tube. The bottom of the Y-tube was covered with sand. As shown in Table 9, the number of macroscopic organisms placed in the test tank varied with the nature of the test. An effort was made to have approximately the same biomass present, irrespective of test species. Specimens of Clibinarius tricolor and Pagurus miamensis from storage tanks were placed individually in the stem of the Y-tube. The test animal's position was observed 5 minutes later, except in cases where the specimen crawled over the cloth partition at the end of each arm before the end of the 5 minutes. If the specimen was still in the stem at the end of the first period, it was left in the Y-tube an additional 5 minutes. If the crab still did not show a choice, it was removed. The sand in the Y-tube was stirred about after each test to eliminate the possibility of trail following. Test replications were separated by at least 5 minutes. The supply tubes from the test and control tanks were alternated after every 10 tests to counteract any position preference of these hermit crabs. The positions of the test and control tanks were also interchanged occasionally. Unless otherwise specified, the tests were run during the day, when crabs of the species being tested normally were aggregated in the field. Chi-square tests were calculated on the distribution of choices between test and control arms of the Y-tube. The results of these tests are shown in Table 9. In all cases, the test and control tanks had sand from the same source covering their bottoms. The results of the experiments, in which individuals of Clibinarius tricolor were tested for orientation toward water which came from a tank containing a group of Clibinarius tricolor, were statistically very significant in both the 1962 and 1963 series. For simplicity, the results are grouped in item number 1 of Table 9. The empty mollusk shells used in item number 4 had formerly been occupied by specimens of Clibinarius tricolor. They were emptied, washed for a number of hours in running seawater, washed in 70% ethanol twice, and then washed in running seawater for another hour. The small number of fiddler crabs, Uca rapax, used, 12, were sufficient to fill the test tank. Even with this small number of individuals, The crabs did not appear to adjust to the clear water, sand bottom, and/or crowded conditions. They were in a highly disturbed state throughout the testing. Limbs grossly extended and rigid, frequent limb autonomy. The specimens had been collected from a mudflat in turbid water that was left in isolated pools during low tide and was presumably subject to temperature fluctuations. Their lack of adjustment to the test apparatus was not as unexpected as was the avoidance shown by individuals of Clibonarius tricolor. Likewise, the strong avoidance of the water coming from the tank containing spider crabs. Mithrax verrucosus was surprising. It should be noted that although these spider crabs adjusted better to the test apparatus, they were constantly fighting actively and/or going through aggressive displays toward one another. For the tests listed in items number 7 and number 8, 1 or 2 detritus-covered rocks were placed in the test tank. These rocks were of the type upon which Clibonarius tricolor normally feeds at night. Tests were run in the morning, 0600 to 1200 hours, item number 7, well before aggregations in the field begin their daily emigration, and in the late evening and night, 1800 to 2200 hours, item number 8, when individuals in the field are spread out over the feeding grounds. The tests of item number 8 were the only ones using Clibonarius tricolor that were carried out during the evening or night. Pilot experiments in 1962 indicated that there is no orientation toward aggregations of Clibonarius tricolor after about 1600 hours. Therefore, the tests for chemical orientations were carried out between 600 and 1400 hours. The same time restrictions applied in the tests with Pagurus miamensis, except that diurnal testing was always stopped before 1200 hours, due to the earlier emigration of the groups of this species. The detritus rocks used were taken from the areas of group formation and feeding. These two areas are less distinct in Pagurus miamensis, in that the crabs feed on rocks in the same faunal ecological microzone that they group in. The tests listed in item number 12 were carried out using a slightly different procedure. A detritus-covered rock similar to those used in the tests of items number 10 and number 11 was placed in the test tank. When this rock was taken from the field, it had 5 individuals of Pagurus miamensis on it. These crabs, plus 85 from a storage tank, were allowed to settle on the rock in the test tank, and this artificial micro-community was undisturbed for over 36 hours before testing was started. Individuals to be tested were taken from the group on the rock. After the first 50 tests, 20 more individuals were placed in the tank and were undisturbed for over 24 hours. Testing was carried out from 500 to 1000 hours in order to maximize the possibility of detection of any orientation tendency. As is seen from Table 9, it was only under these most favorable conditions that a statistically significant chemical orientation was shown by members of this species. The results of these orientation experiments indicate the presence of a number of interesting, chemically elicited reactions. In the first place, individuals of Clibonarius tricolor do orient chemically toward a group of conspecific individuals. This orientation could aid in formation and/or maintenance of the diurnal aggregation. The orientation did not occur at night when the crabs are normally dispersed over the feeding area. However, the orientation was not species-specific, as shown by the reactions given in the tests using groups of Calcinus tibicen. When given a choice, individuals of Clibonarius tricolor showed no preference between a conspecific group and a group of Calcinus typicid. The tests with empty shells, item number 4, indicated that the crab's shell is not important in its chemical orientation toward a group of crabs. No orientation shown, p greater than 0.25. The second and rather surprising set of results was the avoidance of both fiddler crabs, whose limbs were rigidly extended, crabs apparently in shock, and spider crabs, which were continually fighting. These crabs were utilized simply because they were available, representative, non-Pagurids crustaceans. I wished to see if positive orientation by Clibonarius tricolor was limited to members of the same family. The strong avoidance shown tends to disqualify the results for the above-mentioned purpose, but they are of interest themselves. They suggest the possibility that crabs in shock or engaged in a high level of aggressive interactions give off a chemical that other crabs can detect and avoid. Another possible explanation is that some property of the particular species themselves was avoided by individuals of Clibonarius tricolor. The third result was the crab's orientation at night, but not during the day, toward a detritus-covered rock, their normal food source. These tests show that chemical cues are important and multiple in the behavior of Clibonarius tricolor. The tests with Pagurus miamensis showed that this species does not orient toward a group of conspecific individuals, or to the type of rock they aggregate upon in the field. However, individuals did orient toward the combination of these two objects. The latter result most nearly approaches natural conditions, and thus chemical cues appear to be of importance in this behavior in this species.